Okay, so let's jump right into investigative science honors. We're going to be talking about Kepler's laws of planetary motion. So make sure you pause it for a second and get this into your Cornell notebook. Your topic is going to be Kepler's laws of planetary motion, and your learning objectives are going to be I can use my understanding of Kepler's laws to answer questions about planetary motion. So go ahead and get that done. All right. So, Johannes Kepler lived from 1571 to 1630. He was a German astronomer, mathematician, and astrologer. The really important thing is that he talked about the motion of the planets, which previously they thought just went in big circles around the sun. Happens to not be the case, and that's important because if we're going to be sending people to the moon or maybe a rover to Mars, we're going to want to know exactly the motion of the planets so that we don't miss. So, his first law is the law of ellipses. Before this, like I said, we thought that we recorded or we went around the sun in a perfect circle, which isn't the case. We actually, all the planets go around an elliptical path. And it looks just like this. So, on the left-hand side, you're going to have Kepler's first law. You see the sun is on the left, and then there's an X directly opposite, and that's the other focus point. So these are two focus points. One is where the object is that is being orbited, and then the other focus point, nothing's there. It's just a reference point. Now the planet is going to be going around. You can see that at a certain point it's going to be very close to the sun, and then at another point, if you go the opposite end, it's going to be very far away from the sun. That's going to be important when we go into some of the other laws. How elliptical the object is called its eccentricity. It's the amount of flattening of an ellipse or how much the shape of an ellipse deviates from a perfect circle. So it's going to be the focal distance divided by the major axis. And what that means is if I go back, the focal distance is how far away the two focus points are from each other. You're going to measure that distance, and then you're going to divide it by the major axis. And if you look on the right-hand side, you can see that ellipse and that line that goes across its widest point. That is the major axis. If you take the focal point distance and you divide it by the major axis, you're going to end up with something between 0 and 1. If it is 0, that means that there is no distance between the focal points. It means that the focal distance is 0. 0 divided by anything else is going to be 0. So you get a perfect circle. The closer to 1 you get, the more stretched out it's going to be. So as you can see on the right-hand side, that purple ellipse, it is an eccentricity of 0.95. And so it's going to be very stretched out. Okay, and that's how we're going to describe the different shapes of the ellipses in our different orbits. So let's take a look at this problem really quick. If I have two focal points and then the major axis going across through those two focal points, and the focal points distance between the two is 5 centimeters, and the major axis is 8 centimeters, how am I going to find the eccentricity? Go ahead and pause for a second, try and figure that out. Well, you might see that the eccentricity is 5 centimeters divided by 8 centimeters. And when I do that, I'm going to get an eccentricity of 0.625. So it's not a perfect circle, but it's also not super stretched out. It is moderately eccentric. This table shows us the different orbital eccentricities of the different planets. So you can take a look at those and kind of tell if you take a look which planet has the least eccentricity, has the lowest value. I want you to make note of which one is the most circular in its path. And then which one is the farthest away from being a circle. Take note of that as well. So aphelion and perihelion are two different points. Perihelion is going to be when the planet is closest to the orbiting object, so the Earth to the Sun, when it's closest, and the aphelion is going to be when it's farthest away. Okay, we're going to continue on with second law after this.